to the third part of the mini course, of the goal. So this is what I stated as section 3 for the mini course, which is to prove the following theorem. So this is due to Mori, that gives a geometric sufficient condition for uniruledness. So namely, so let X be a smooth projective variety defined over K, an algebraically closed field. And then if X is Fano, meaning the anticanonical class is ample, then X is uniruled. In fact, we will prove a bit more. We will prove that given any point of X, I can find a rational curve of degree bounded by some number that depends only on X. So let me state this for any, so through any point of X, there exists a rational curve C such that the anticanonical degree of C is bounded by the dimension of X plus 1. So the proof, this is a very interesting aspect of this proof. You may be interested, for instance, in complex projective varieties. So here you would take K to be C. And you maybe would like to have a proof that applies only analytical methods. But in fact, as far as I know, there is no proof for this statement that does not go to positive characteristics. So the proof will go through positive characteristic. So it would be very interesting to have a proof that works within the complex numbers. Okay, so we want to produce rational curves on a given variety. So how do we do this? So there are two very important lemmas that will help us produce rational curves of bounded degree on X. So these are what we call the bend and break lemmas. So let me state them. So first, bend and break 1. Says the following. So let me fix, for this, let me fix K, an algebraically closed field of any characteristic. So the bend and break 1 says the following. So suppose, so again, let X be a smooth projective variety, everything over K. Let me fix a point X in X, and let C be a smooth proper curve, and let me fix a point P in C. If there exists a morphism, so if there exists, so suppose there exists a smooth curve B. So this B is not necessarily proper, but we assume there is a smooth curve B and the morphism F from B times C to X with the following properties. So I want to see this B as parametrizing a family of morphisms from C to X. So the first thing I want to require is that for every such morphism, the point, the distinguished point P is sent to X. So I ask that F of B cross P is the point X. Now I also ask that this morphism is not trivial, meaning I could start with one morphism from C to X, and I could just compose this with the first projection. So I do not want this, so I will require that the image, or maybe the way I should say it is that Ft is different than Ft prime for general T in B, where Ft is just F restricted to T cross C. So what is happening, what the hypotheses are telling me is something like this, that I have a bunch of morphisms from C to X. They all send a T to X. And the image is a surface. And now what the conclusion says is the following. Then the family of curves Ft of C degenerates into a curve containing a rational component through the point X. So this is saying that if I am able to find a deformation of the morphism from C to X that moves keeping this one point fixed, then in the limit, this curve will break to produce one rational curve through the point X. So this is the picture. So this is the first bend and break lemma. It gives us a way of producing a rational curve on X. Now we have the second bend and break lemma. Which says the following. So let X be a smooth projective variety. Actually, for those statements, I don't even need X to be smooth, but I will only apply in this case, so I'll just keep this. So X will be a smooth projective variety. Again, I will fix 2 points, X, Y, in X. And I will assume, so suppose there exists a smooth curve B, again, not necessarily proper. Such that in the morphism F from B cross P1 to X such that, well, first of all, so I want to think of this as a family of morphisms from P1 to X. And I want to ask that this family of morphism has the property that the points 0 and infinity are always sent to these two fixed points, X and Y. So I ask that F of B cross 0 is always the point X. F of B cross infinity is always the point Y. Now notice that, again, I want to say that this morphism is not trivial. So here I only asked that Ft is different than Ft prime for general, T and T prime in B. Here this is not quite enough because I know that I have a one-dimensional family of automorphisms of P1 keeping X and Y fixed. So in order to avoid playing just with automorphisms of P1, I will require that the image of this surface is two-dimensional. Then the conclusion is the following. So geometrically what is happening is that now I have a family, now I already have rational curves, but I can deform them keeping 2 points fixed. So the conclusion will be that in the limit, this family will break into a curve that is non-integral and has rational cycles. Then the family of curves will degenerate into a non-integral curve with rational components. So the point here is the following. If I start with a family of curves through these 2 points that moves in X, in the limit I will produce rational curves through X and Y with degree less than the degree of the original curve. Because this limit curve will be non-integral. So this is the way that I can guarantee, I'll be able to guarantee that a Fano variety has rational curves of bounded degree. Okay, so I will postpone the proofs of these 2 theorems for a bit later. And first I want to explain how we will use them to prove Mori's theorem. So let me recall from yesterday some elements of deformation theory. So we started with X, smooth projective variety. C will be a smooth proper curve. and F is a morphism from X to Y. So we are interested in studying morphisms from C to X. So we saw yesterday that there exists a space, a scheme, K-scheme, morphisms from C to X, parameterizing such morphisms. And moreover, we saw the following. We gave a local description for this space. So we saw that the dimension, so the tangent space to this scheme at a point corresponding to a morphism F is isomorphic to H naught of C, pull back the tangent bundle. Second, if the H1 of C pull back the tangent bundle is 0, then this scheme morphisms from C to X is smooth at the point F. So in general, in fact, what we have is that this space at the point F is cut out by this, the dimension of this space, equations in a smooth space of dimension H naught. So in general, what we have is that the dimension of the space of morphisms at the point F has a lower bound, which is the H naught minus the H1. Now, as I mentioned, this is just the Euler characteristic of the curve, of this vector bundle on the curve. So this is just the Euler characteristic of the pullback of the tangent bundle, which can be computed using Riemann-Roch, and this will be the degree of the vector bundle. So this is minus kx times the curve plus the rank of the vector bundle, which is dimension of x, times the Euler characteristic, which is 1 minus the genus of C. And let me just make a remark that I forgot to say yesterday. As I mentioned, this space in general has infinitely many irreducible components. So in particular, it is not quasi-projective. However, if you fix the degree of the curve, then this becomes quasi-projective. So if we fix H, an M-poline bundle, on X, and D, a positive integer, then we can define the space MD C to X to be morphisms from C to X whose degree with respect to H, say, is less or equal than D. Now, if I fix this, then this becomes quasi-projective. So in general, we have infinitely many components because we have curves of higher and higher degree. Okay, so now, as you see by looking at the bend and break lemmas, sometimes we are interested in not only studying the formation of morphisms, but we are interested in the formation of morphisms with some prescribed fixed structure. For instance, here we want morphisms that send the point P to the point X. And in the bend and break 2, we are interested in morphisms that send 0 to X and infinity to Y. So in general, if we can fix Z in C, a closed subscheme, and say H morphisms from Z to X, sometimes we may be interested in morphisms F from C to X that extend this given morphism H, such that F restricted to Z is H. Now, so for instance, in bend and break 1, we want Z to be the fixed point P, and H the morphism that sends P to X. Or in bend and break 2, we can take Z to be morphism, Z to be 0 and infinity, and H to be the morphism that sends 0 to X and infinity to Y. Okay, so then, in fact, what I wrote there remains. We still have a scheme that parameterizes morphisms with this extra structure, and they have very similar properties as the ones that I stated. So let me, I'll have to erase the lemmas. And as before, there exists a scheme which I would denote scheme of morphisms from C to X extending H. Parameterizing such morphisms. And then the same local description holds. So I think I will be more interested, well, let me state them all. So again, the tangent space to a given morphism, X of this space of morphisms, is isomorphic to H naught C pullback of the tangent bundle, but now I have to twist it by the ideal sheaf of C. So remember, we had this picture, we had this morphism from C to X. And this vector bundle, pullback of the tangent bundle, you can think of it as a certain vector field on the curve. And this is exactly the first order deformation to a certain deformation of this morphism, if it exists. So now, when we require that Z is kept, the image of Z is kept fixed, is saying that, if for instance this Z is a point, then this vector field must vanish at this point. So this is why we get this the ideal sheaf here. Again, the H1 is what controls the obstruction for a first order deformation to actually come from a deformation. So if the H1 of C pullback of T sub X is 0, then the space of morphisms from C to to x, keeping h fixed, is smooth at the point f, and thus it will have exactly dimension h0 of that vector bundle. And in general, the dimension of this space at f will be greater or equal than the h naught of C pullback of Tx twisted by the ideal sheaf of C minus the h1 of C pullback Tx twisted by the ideal sheaf. And then again, you can write down Riemann-Roch, and then you will get that this number is equal minus kx times f of C. And then here, the length of this subscheme Z will come into the picture. So what we will get is that lim x 1 minus GC minus the length of C. And also, as for the first case, this space of morph, this scheme comes with a universal morphism. Okay, so now we will use this, and let's see how we will try to use this, put these things together to produce rational curves on Fano. So let's assume now that we have a Fano manifold So we have a Fano variety with minus kx ample, and we want to produce a rational curve through a given point. So let's fix a point x. So what is the idea? For sure we can produce some curve, even a smooth curve, through x. So normally you can just take, for instance, hyperplane sections. So you can find a smooth curve C, contain the point P, and a morphism F from C to X, sending P to X. So what is the idea? We want to apply bend and break 1. To apply bend and break 1, we must be able to deform this morphism with one point fixed. And if we are able to do so, then in the limit, we will get a rational curve through x. So in order to produce a one-dimensional family of deformations of f, we will use this estimate on the space of morphisms that send the point P to x. So our estimate says the following. So the dimension at the point f of the space of morphisms from C to x that send the point P to x is greater or equal than the anticanonical degree of the curve and then here the length of z is exactly 1, so what we get here is minus the genus of the curve times the dimension of x. So what we would like to say is that this number is positive. So if this is greater than 0, then bend and break 1 will give us a rational curve through X. So remember, if this is 0, that means that I can find some curve in this space of morphism, and then I can just look at the universal morphism, and I get exactly a family of curves that keep one point fixed. Now, of course, if the genus is already 0, then we are done, and if the genus is non-zero, then we cannot have an automorphism of the curve with one point fixed. So, in fact, we get a non-trivial family of morphisms. So, what we want to say is that this dimension is positive. Now, we have this condition here that forces this part here, this factor here to be positive. However, if the genus is greater or equal to 1, then this part here is negative. And then we can't say anything. So, okay, so let's see what we can do in this situation. How could we fix this? Okay, so if the genus of this given curve is 0, then okay, then we already have a rational curve through the point X. Now, what happens if the genus of C is 1? Well, if the genus of C is 1, then we can play a trick. In this case, so this is an elliptic curve, so we know that there exists an endomorphism phi from C to C that is just given by multiplication by M. So this will be an endomorphism M squared to 1. So we get a finite morphism of C into C of degree M squared. And now if we take F prime to be the composition of F with this morphism, and now we apply this estimate to F prime, then what we get is the following. So we get that the following lower bound for the space of morphism at this new point F prime. So this will send perhaps a different point P prime to X. This will be greater or equal than, now this degree here will be M times M squared times the original degree. But now the genus remains, so what we have is minus GC times dimension of X. So we see that because this number is positive, if we take M large enough, then this number, this is fixed. This does not depend on M. So if I take M big enough, this part will be positive, and then I'm done by bend and break 1. So by taking M sufficiently large, we get that this is positive, and we can apply bend and break 1. Okay, so we were able to play this trick. And now let's see what we can do for higher genus. So now what happens if the genus of C is at least 2? Well, then the same trick does not apply. In general, we don't have such endomorphisms. So we could try to do something different. Even though we don't have endomorphism, we still have finite morphisms. So we could take, say, a finite morphism from C prime to C. And then try to do the same trick. But the problem is that now, if I take the finite maps, then the genus of C prime is not equal to the genus of C. So even though we will increase this part here, we are probably going to increase this part, decrease the negative part as well. So for instance, let me just give an example. Let me take a, say, M to 1 map, and let's assume it's a tau. Oh, then Horowitz tells us that the 2G C prime minus 2 will be M times 2G C minus 2, so that the genus of the new curve is going to be M GC minus M plus 1. And now if we take F prime to be F composed with phi, so this is a morphism from C prime to X, then the lower bound that we get is the following. So the dimension at the new point F prime of the space of morphisms from C to X that send certain P prime to X will be, so again, this part here gets multiplied by M. And then we have to, now we have minus G prime, which is this thing here. So we get, so in the end, if we substitute in the formula, we get that minus M times GC minus 1. So we see that even though this part here increases with M, this part here will also increase linearly with M. So we cannot guarantee that this will become positive. So taking, for instance, et al. Covers does not do the trick if the genus is at least 2. And then we have to think, what can we do then? And then we have to remember Stefan's lectures in the morning, where he's exploring the Frobenius morphisms. So in characteristic P, we do have endomorphism of the curve C of degree greater than 1, which is given by Frobenius. So let's assume now that the characteristic is positive. So assume the characteristic of the base field is P. Then what we can do is the following. We can look at the Frobenius map from C to C. So this is a degree 2, well, it's 1 to 1 at the level of sets, but this is a degree P map. And so now we look at the composition of F with F to the M. So let me call it Fm. And now what the lower bound gives us is the following. So the first part, the positive part, gets multiplied by P to the M. But the second part remains the same because we don't change the genus. So you see that if we take M big enough, then this part will be greater than the genus times the dimension. So we get that this is positive. And then bend and break 1 gives us a rational curve on X through the fixed point X. Okay, so maybe I will keep this for the moment. So what is the conclusion? Is that pretty much we proved Mori's theorem in positive characteristics. So the conclusion is the following. So we have proved so let X be a smooth Fano variety over K, an algebraically closed field with positive characteristic. Then X contains a rational curve through every point. Well, it's still maybe not obvious from here that we actually get that X is uniruled. So remember, a variety is uniruled if we can find a dominant morphism from dominant map from Y cross P1 to X. Here the dimension is 1 less than dimension of X. And so in a sense, we want these rational curves all to live in the same family. So we just produce one rational curve through every point, but in principle, if the field is uncountable, if the field is countable, they could not fit all in a single family. But we will fix that in the following lemma. So again, here we have a characteristic, now arbitrary characteristic. So X is smooth projective variety over an algebraically closed field. So assume that X has a rational curve through every point. Then, in fact, it has a rational curve of bounded degree for every point. Then for every, then it has a rational curve C C of degree bounded by dimension x plus 1 through every point. And to prove this, we will basically apply the second bend and break lemma. So proof. So we fix now x in x, and the morphism, non-constant morphism from P1 to x, sending 0 to x. So the idea is the following. So let me give a name y to f of infinity. And let's look at the dimension at the point f of the space of morphisms from P1 to x, sending 0 to x and infinity to y. So the idea is that if the degree of this curve is too high, then we will find a suitable curve in this space of morphism that will allow us to apply bend and break 2. So let's estimate this dimension. So this is greater or equal than the anticanonical degree of the curve plus, now here we have genus 0 and length 2, so we get minus dimension of x. So we notice that, okay, so if this number here, minus kx, so if the degree of the curve is less or equal than dimension of x plus 1, then we are done. Because the goal is exactly to produce a rational curve of degree bounded by dimension plus 1. So if this bound is achieved, then we are okay. So if not, so if this intersection number is at least dimension of x plus 2, then this estimate becomes the following. So then the dimension at f of the space of morphisms from P1 to x, sending 0 to x and infinity to y, is going to be at least 2. Now notice that here we have the automorphisms of P1 that keep 2 points fixed. So we have the automorphisms of P1 that keep 0 and infinity fixed. And this has dimension exactly 1. So this will account for one dimension here. But we have this space at least 2-dimensional, so that means that we can find a 1-parameter family of morphisms from P1 to x whose image is a curve. So we can apply bend and break 2. So we produce a family of morphisms from P1 to X that keeps 2 points fixed. And then in the end we conclude that we can find a rational curve through X of degree smaller than the degree of the original curve. So we conclude that there exists a rational curve through X of minus kx degree smaller than the original one. So let me give names to this. Well, let me just say dimension of X plus 1. So what we get is that we get a rational curve of anticanonical degree less than the original one. If this is still bigger than dimension of X plus 1, we do the same trick, and in the end, after finitely many steps, we obtain a rational curve through X of degree smaller than the dimension of X plus 1. So this proves the lemma. And so let me make just a remark that this bound in this lemma is optimal so remark the bound of the lemma is sharp. So you just have to see that you just have to take X equals to Pn, then the anticanonical degree of a line is exactly n plus 1. And it's actually a very deep theorem, very nice theorem that says that this is the only case when this bound is sharp. So I'm not going to talk about this here, but so that you know that Pn is the only variety for which this bound is always sharp. Okay, so once we have rational curves of degree fixed by dimension plus 1, we see that in this proposition we improve it. We actually show that X is uniruled. So the lemma implies that is now in characteristic P greater than 0, X Fano implies X uniruled. Now we really have curves of bounded degree for every point. So they have at least some. Most of them will fit in a family. So we'll get a family of rational curves that sweep out a dense open subset of X. Okay, so now, we are interested in what happens in characteristic 0. So we've proved the result in characteristic P. And now we have to lift it to characteristic 0. So I will just give you an idea of how this can be done. So now let's look at the proof of Mori's theorem. So let X be a Fano variety. So over K, an algebraically closed field. And now, by the proposition and the lemma, we may assume that the characteristic is 0 And what we have to do is to produce a rational curve through every point. Or for a general point. Now this is sort of standard. What we have to do, so let me simplify the situation here. So for simplicity, we will assume that x is defined by equations with coefficients in z, and they will perform reduction mod p. So first let's start by we'll have to embed x in some big projective space. So we pick M such that M times the anticanonical class is very ample. So we use it to embed x in some big projective space, Pn. And for simplicity, we will assume that x is defined inside Pn by equations with coefficients in z. So for simplicity, let us assume that x and the point, we need also the point x. So that x and little x are defined by equations in fact, I want a bit more. I want that the x is defined. Okay, x and x are defined by equations with coefficients in z. So let's say that x will be defined by a bunch of equations h1 of x naught to xn equals 0 up to hr x naught xn equals 0. And I will also assume, in fact, what I want to assume is that the coordinates of x are also given by integers. So let me fix it. H naught hn. So I assume that all the coefficients of the hi's and all the ai's are integers. Okay, once we have this, we will be able to do reduction mod p and then apply the proposition. But before we do so, let's see what we want. What we want to find the rational curve on x containing x of bounded degree. So what we want is to say that there exists, so we want the following condition. There exists a rational curve to x sending, say, 0 to x such that minus kx dot fp1 is less or equal than x minus 1 plus 1. So we want it to be non-constant. So what does that mean in terms of equations? So this f will be given by n polynomials n homogeneous polynomials of the same degree. And so this condition says exactly that there exists homogeneous polynomials g naught up to gn of degree bounded by m times dimension of x plus 1 such that so we want that g I of 0, say 1 0 is ai for every I, and we want that the hj of g naught up to gn is identically 0 for every j. Okay, but this, so this is equivalent. So if you write down these conditions in terms of the coefficients of G, what you get is a certain system of polynomial equations, certain homogeneous system of homogeneous equations. On the coefficients of the GI, and these have integral coefficients. Has a non-trivial solution. And now, so by elimination theory, you can actually rewrite this by saying that a bunch of polynomials in the coefficients of a GI must vanish. So I do not want to get into details, but now what we see is the following, is that what we know, we start with our variety that is defined over the integers, x. So x in P and K is defined over Z. Now what we can do is that we can take for every P prime, we can consider a variety xp defined in the algebraic closure of fp exactly by the same equations, but now mod p. So in general, you cannot say that this will always be a smooth projective variety, but for infinitely many p's, xp will be a smooth Fano variety and then by the lemma in the proposition we find a curve through X, a rational curve of bounded degree. But this implies that the system of equations S, when we reduce mod P, has a solution. A non-trivial solution for almost every P. But now if it has a solution for almost every P, then it must have a solution defined in K. So this way we produce a rational curve on X. And we're done. So this is a very common trick. If you can sometimes produce solutions for infinitely many primes in a bounded way, then you can leave this to characteristic 0. So what remains to do now is to give a proof of the Algebraic lemmas. Actually, I should make a remark that I made this very strong assumption that both x and little x were defined by equations with coefficients in z. So I should at least say what you have to do in the general case. So in the general case, so the coefficients of the hi's and the coordinates of x may not be all integers, but they will lie in some finitely generated ring over Z. So the coefficients of the hi's and the ai's lie in some ring R finitely generated over Z. And then if you take any maximal ideal M in R, then the quotient R over M is a finite field. And so you just repeat the same argument, but instead of doing reduction mod P, what you do is a reduction mod this maximal ideals, and then the same argument goes through. So to finish, so perform reduction mod M instead of mod P. So in order to finish, let's then prove the bend and break lemmas. So the first bend and break says, let me remind you, that we had a curve, a smooth curve, not necessarily complete B, that is parametrizing morphisms from C to X. And we assume that there is a fixed point P in X that is sent to a fixed point X in X. We assume that F of B cross P is a fixed point X, and we assumed also that F T is different than F T prime for general T and T prime in B. So here Ft is just F restricted to T cross C. And now what we want to show is that in the end, this family of curves will break and produce a rational curve. Okay, so now let us take some smooth compactification of B. So we have a following diagram. So we have here we have B prime. Here we have C, B bar, and then we have the product. And now this morphism F will give us a rational map to X. And we know that it will not be defined at most at finitely many points. So the first claim is the following. So here is our point P. So we have this section here, sigma P, which is P B cross P, B bar cross P. And the first claim is that F is not defined at some point in this section. So we know that, so the claim is that F is not defined at some point, say Q, on sigma P. So let's prove this claim. Okay, so so let's assume otherwise. So we assume that F is defined in a neighborhood of sigma p. So the points where it's not defined lie outside of this section. And then we can take, so since there are only finitely many, if I take a general point C, this morphism would be defined also in this section. So if C in C is a general point, then F is also defined on a neighborhood of sigma C. But then this will tell us the following. If we fix an ample line bundle on X and look at the pullback to this section, it will be 0 because this section gets contracted to a point X. So let me write this. So if yes? B, the base is not necessarily compact.
So if it is compact, that will be defined everywhere.
Yes, but then we will see that will not be able to, if the curve C has genus 1, this cannot occur. We are assuming that we have this section that gets contracted to a point. So if it is defined everywhere, what we will see now is that every such section is going to be contracted by a point, so the image will be just a curve. And this will contradict this part here. So, well, assuming that the genus of C is at least 1. So let H be an ample line bundle on X. Then since sigma P is mapped to a point X, then we have that the pullback of H dot sigma P is 0. But now we see that if we shrink C if necessary, this projection, this is a flat morphism, and this will tell us that this intersection number with F, pullback of H, must be constant. So the pullback of H intersection with sigma C will also be 0, where C is general. But this will imply that F of sigma C is constant. So this is a point for C general. So we get that, but this will contradict. So Ft will be equal to Ft prime for general T prime in B, as long as so the genus of C is 0. So this is because if this is true, then for a general point of B, the image of the morphism will be the same, but since it sends always the point P to X, and there's no automorphism with one point fixed if the genus is greater than 0, then in fact we have that Ft equals to Ft prime. So this contradicts assumption 2. So this proves the claim. So the conclusion is that this morphism is not defined in at least one point of this section, say a point Q. Oh, and possibly at other points. But now what we will do is the following. We will resolve the indeterminacy of this map so we can find a surface by blowing up the indeterminacy points and finitely many points above them. We get an S that is fibered over B bar and a map that that resolves the indeterminacy. But let's see what happens at this point. So we necessarily have to blow up this point Q. So here is the fiber over Q. And when we do that, so we get an exceptional divisor, well, maybe a bunch of exceptional divisors over this point and possibly over other points. And at least one of these curves, so these are all rational curves. So each component that appears here are rational curves. So these are isomorphic to P1, each of the exceptional curves that appear there. And at least one of them must survive, otherwise the map was originally defined over Q. So by this we see that at least one of these P1s is mapped birationally onto its image, and the image must contain the point X. So by resolving the indeterminacy of F, we see that there will be a rational curve on such S mapped non-constantly to X. And the image will contain the point X. So this proves bend and break 1. And the proof of bend and break 2 is very similar. So let me quickly sketch it. So proof of bend and break 2. So let me recall the assumptions. So again, we had a possibly non-complete curve B. We had a P1 cross, so we had a map F from B cross P1 to X with the properties that F mapped B cross 0 into a fixed point X and B cross infinity into a fixed point Y. And we assume that the image of this morphism is a surface. Then we want to show that this family of P1s that keeps these 2 points fixed in the end will degenerate into some non-integral curve. So what we do is, as before, we take B bar. Maybe I'll use that drawing there. So we let B bar be a smooth compactification of B, and S to B bar be a P1 bundle that extends the B cross P1. You can just take the product here if you like, but we will apply sort of induction, so we will need to consider general P1 bundle. So we have a situation like here. Okay, maybe it's easier if I do a picture again. So we have the smooth compactification B prime, and here we have a P1 bundle S over B bar. And a map, now a rational map from S to X. So here we have 2 sections. We have a section, well, we have many sections, but 2 distinguished sections, which is the sigma naught and the sigma infinity. So sigma naught and sigma infinity are sections extending B cross 0 and B cross infinity. So the first claim is that this F cannot be a morphism. So F is not defined everywhere. And as in the previous case, we proved this by doing intersection theory on surfaces. So assume otherwise. Then we know, since these 2 sections here get contracted to X and Y, then the Hodge index theorem says that they have a negative self-intersection. So since F of sigma naught is a point and F of sigma infinity is also a point, their self-intersection must be negative. Now, this is impossible because this is telling us that sigma naught, sigma infinity, and say something, the pullback of something ample, are linear independent but we also know that since we have a P1 bundle over a curve, we know that the Picard number of S is 1. So we get, sorry, it's 2. So we get a contradiction, and this proves the claim. Here we are using the fact that the image is a surface. Okay, so we know that this map is not defined everywhere, so we will need to blow up some points in order to resolve the indeterminacy of this map. So now there are some cases. So suppose we have to blow up a point here. Let me give a name for its fiber. Let's say L. So if we have to blow up 2 points that lie in the same fiber, then we are done, because again, we will at least one component of the exceptional locus over each of these points will be mapped birationally onto its image in X. So here we resolve the indeterminacy. S prime. Call this map F prime. So let me write this. So there are basically 3 cases. So case 1, we need to blow up, so F is not defined. At 2 distinct points of some fiber L. So in this case, there will be at least 2 distinct components of pi prime minus 1 of t. So I will call this map is pi. This map here will be pi prime. So that we find at least 2 distinct components, irreducible components of this fiber that are mapped non-constantly into X. So this means that when we look at the family of original rational curves parameterized by B, in the limit at this point t, we will have at least, well, we could have, there will be 2 components that are mapped non-constantly. They can either, say, map into 2 distinct curves, or they can map into the same curve, but then it will be non-reduced. So this way we get it's non-reduced, non-integral. here is a P prime. Okay, so this is the first case. Now in the second case, so we get that F, we assume that F is not defined at one point of L, and F restricted to L is not constant. Then again, we have the same conclusion. We will have the strict transform of L and plus at least one more component that are mapped non-constantly into X. So we are done. And then finally, case 3, which is F, is not defined at one point of L, but F restricted to L is constant. Then let's see what we have to do in this case. Okay, so we do the following. We have the B bar. We have one point here that we have to blow up. Let me call it Q. And we assume that F contracts this curve L. So when we blow up this point, just blow up it once for the moment, then we get an exceptional curve E and the strict transform of L. And here we still have a rational map to X. Now this becomes a -1 curve, and F, or the induced map, is still constant on L tilde. So that means that we can contract L tilde and get another surface S prime with a rational map to X. So let me call this S prime. So this was S. So now we still are in the same situation as before. We still have a surface that is a P1 bundle over B bar, but notice that now we need one less blow up to resolve the indeterminacy. So now we just applied induction on the number of blow-ups that are necessary to resolve the map. So let me write this down. Then can blow up this point and contract the strict transform of L and in this way we get a new P1 bundle S prime over B bar extending B cross P1. And we need one less blow-up to resolve in the determinacy of F from S bar to X. And so we conclude by induction on the number of blow-ups. So this proves bend and break 2. Okay, so this is at least an idea of the proof of Mori's theorem, and then tomorrow we will continue with some other properties of uniruled varieties and maybe rationally connected varieties. So I stop here.